All right, welcome everyone. We're very lucky to have Tai-Danae Bradley here with us today. Tai-Danae Bradley is a mathematician who received her Ph.D. in mathematics from the CUNY Graduate Center. She was formerly at Alphabet and is now at Sandbox AQ, a startup focused on combining machine learning and quantum physics. Tai-Danae is a visiting research professor of mathematics at the Masters University and the executive director of the Math3ma Institute, where she hosts her popular blog on category theory. Last but not least, she is a co-author of the textbook Topology, a categorical approach that presents basic topology from the modern perspective of category theory. Welcome, Tai-Danae. How are you today?
I'm good, Tim. Nice to be here. Thanks for inviting me.
Oh, great to have you. It's always great to connect with another mathematician, and you're also in industry. You were at Alphabet. I'm still at Alphabet, but it's great to see that you're continuing to do great things. Maybe we can start by you telling us about your background a bit, because it doesn't fit into any nice conventional mold. I mean, most people who get a math PhD either go straight to academia or they go into a job that's more traditional for someone with a mathematics background like finance or statistics or data science. But you're neither of those. So can you tell us how you got onto your current path?
Yeah, it's a great question. Thanks for asking that. Yes, it's true. I've not taken this either or, but I kind of found a nice place that's hybrid in the middle, which I really enjoy. And I think that actually started when I was in graduate school. So as you mentioned, I got my PhD at the CUNY Graduate Center in the pure math department, in the pure math program. But my research for my PhD wasn't really strictly pure math because it was very much motivated by sort of a more applied problem. So when I was in grad school, my thesis advisor, John Torilla, was interested in using tools from mathematics and quantum physics to kind of tackle problems in a problem in machine learning, in particular in the space of language. And I think that was my first introduction to kind of approaching pure math, but in a non-traditional way. And even using, kind of non-traditional math like category theory in a way that, folks maybe don't typically think of it as being applied. And I really enjoyed that. Learning tools that maybe don't seem to have any application in the real world, but then having that freedom to kind of be creative and think and see those structures and patterns outside of mathematics. I really enjoyed that. And so after grad school, I was very fortunate to be on a team of people that also really appreciate these sort of going back and forth between industry and academia. And so I was able to find a really nice spot there and have been doing that kind of work ever since.
All right, great. So we're going to do a pretty advanced topic today. We mentioned in your bio category theory quite a few times, so it's no surprise that's what we're going to be talking about. Actually, maybe just some background. How did you get interested in category theory? What motivated you to study it? Because it's one of those things where it's not something that your typical person will come across. Only mainly pure mathematicians, maybe some computer scientists, but I think your typical person, they will have heard about analysis, geometry, combinatorics, but not necessarily category theory. So how did you bump into it, so to speak?
Yeah, I think it's pretty standard to at least bump into those words when you're in a math PhD program, or especially pure math. You kind of can't get away in any class without at least hearing the word category or functor in some sense by either a professor or just a classmate. But yeah, I mean, there's no class, at least when I was in school, there was no one semester course called category theory, but these tools were always cropping up, in various classes. And I think it's like the language of modern mathematics. So if you progress far enough, eventually you're going to run into it. I will say the first time I was in class, I think like my first semester of grad school, I was in an analysis class and reading like the notes or a book or whatever. And then there was like the definition, category, functor, blah, blah. And I remember thinking, this is the worst. This is so dry and confusing and boring. And this is why people don't like math. That's what I thought. That was kind of my first impression of it. Now, it wasn't until I had a really great advisor, my thesis advisor, who thinks category theoretically, which is like very conceptual, or seeing how things are related, or looking for bridges or connections between branches in math that maybe don't feel related initially. And that kind of bird's eye view is a very kind of categorical bird's eye view. So when I started to see category theory in that light, rather than just like, oh, here's a definition, here's some examples, let's move on, but to actually see it in action and to see how it allows you to have a new perspective and to notice relationships and connections that maybe your eyes can't see otherwise. I think that was very transformative for me. And I've always been that like this kind of person that I really enjoy looking at things from a high level. I really love the bird's eye view of things. I remember when I was an undergrad, I remember group theory was such an exciting class for me because it was so abstract. I mean, it was abstract compared to like calculus and even to linear algebra, which I had. And I thought, this is the best. This is so exciting. You know, we're like stripping away the details and just looking at structures. So when I learned that there was like something even more abstract than, you know, group theory called category theory, it was very much, you know, like a flavor that I really enjoyed. So that's how I got introduced, really through my advisor. I think the way that he taught it really opened my eyes, just having a good teacher from that perspective.
That's great. It's always wonderful to hear how much having a great teacher can make a great difference, and it sounded like that was true of your case.
Definitely, yeah.
Awesome. Well, maybe let's just go ahead and get started here. I thought we should always start off with maybe an outline of what we're going to talk about, even though that's always maybe a little bit dangerous because we might we might not get to everything or we might be rushed at the end. But let's go ahead and start out. So I thought what we do. So first of all, let's have a very gentle introduction of what category theory is, because again, most people haven't heard of it, and it really is a nice language for things. So we're going to start kind of gentle with just the basic setup of category theory. So basically all the basic definitions and lots of examples, of course. The second part, we'll get to one of the most foundational results in category theory, something called the Yoneda lemma, although I guess it's also called Yoneda theorem. I don't know, is it a theorem or a lemma to you?
It's a theorem for sure.
Okay.
But we call it the lemma, so.
Okay, I think Wikipedia it's lemma, so maybe we'll keep it as lemma for sake of consistency. Okay, all right. Okay, I guess we'll get to what the Yoneda lemma in due time. It's one of these like meta results, right? It's like it's like you have to do like a mental yoga to think about it.
This is true.
Yeah, it's quite well, it's pretty cool. And the third part will be, I guess, applications to natural language processing. This was actually the draw I had to your work because, for me at least, not being a category theorist, I'm not so interested in studying category theory for its own sake. But when I heard you, for example, on Sean Carroll's podcast, that's how I first became familiar with your work, I was very surprised, pleasantly surprised to see that it was applicable to natural language processing, which is now a very active and big area in machine learning, what I do right now. So yeah, I thought that was cool. Of course, you also talked about entropy, but you know, well, I guess we probably don't have time for that. This is enough to cover. But yeah, I just thought it would be cool to see an application of all this. And I guess the Yoneda lemma is going to play a very critical role.
Yeah.
So I think that's actually really good because you know, studying the Yoneda lemma for the sake of itself might not be so appealing for the broad public, but if we can tie it to NLP, I think that'd be a great way to see the application.
Yeah, great. I think this sounds like a good plan. You know, it's only 3 things, but those 3 things are a lot. So
oh yeah, it's a lot.
This is actually ambitious.
Yeah, we're compressing, you know, graduate course material over weeks or months into a podcast, but you know, it's good to be ambitious.
Yeah.
Okay, well let's go ahead and get started then. Do you want to start us off? What is a category? Why should I care about category theory?
Yeah. Okay. Here's how I like to describe category theory. Currently, I think there's lots of ways to motivate it. One way that I like to think of category theory is like the Mad Libs of mathematics. So you know these Mad Lib stories?
I think so, but I refresh my memory.
Okay, so it's like a fun little like puzzle book or something. I don't know. You have a book, it's got this story, but some of the words are missing. So you're supposed to fill in the words based on like the part of speech. Okay, you know, I went to the blank to buy some blah blah. Okay, in the blank you're supposed to put a noun. The blah blah you're supposed to put a noun, whatever. So in that sense, you know, it's a fun game because depending on which words you put in, you can like read it and it's really funny and bogus and you laugh and have a good time. But the idea is that you have some kind of overall structure or overall narrative. And based on which words you put in, okay, the overall narrative is kind of the same, but the story is different in each of these special cases because your words are a little bit different. Or it's like a template. So whoever wrote the book has given you the template and you fill in the blank, you put in the words, and based on which words you put in, you get a different story, but like the overall skeleton is the same or the flavor is the same. So I kind of think of category theory as like that for mathematics. In mathematics, you realize you're kind of doing the same thing in different branches of math, in differential geometry and topology and analysis and group theory, algebra. You're kind of all working with the same types of tools. And maybe you're dealing with the same constructions, you're building kind of similar things, but they feel very different because of the specific details in that realm of math. But if you kind of like squint or look at it from a coarse grain perspective, you see everyone's kind of doing the same thing. So you have this feeling, but category theory is a language that allows you to formalize that theorem, that feeling.
Yeah.
But it's not just like words, it's not just a language. That language itself is also mathematics in its own right. And so that's what category theory is.
Maybe a good example, I just thought of this, but of course it's probably not due to me, but just as I was thinking about this, it's sort of like object-oriented programming, right? You have objects, you have maps between them, and then of course there's the whole paradigm of what it means to be a language itself. So you can talk about objects, and then you could step back and say, let's talk about programming itself, right? And you get that flavor in category theory. It's very analogous, right?
Yes, it is. It's analogous. Now the thing is, though, I think at least for me, as I was saying, my first introduction, I didn't quite have the benefit of that intuition. So it was just like, here's the definition of a category. And when you look at it, it's just very blah, you know, you've got some stuff and blah, blah, and then whatever. So I think, you know, maybe we could look at the definition, but as you were saying, lots of examples probably help, I think, crystallize these more abstract things. So here's a definition. So A, category C, consists of the stuff we were saying. So you have objects. You know, these are things like, I like to draw them as amoebas, maybe not the best thing, but you have objects, call them X, Y, Z, whatever. And then for every pair of objects, X and Y, you would like to have a way to go from one to the other. So, you have a set, I'm going to leave a blank space for a second, of what we call morphisms, between objects. So typically this set, if the category is called C, the set of morphisms or ways to go from X to Y is denoted by C, X, Y, or some people write, I'll say here, or Hom X, Y, or some people write Hom sub C, of X, Y, to remind us that the category is in C, but these are all notations for the same thing. So you have a set which has the different notations. I will probably not remember which we are using in this conversation, but for now, I'll use C of X, comma Y. So a set of morphisms, you know, for every pair of objects, X and Y, and then you'd like these data to satisfy some nice conditions. So, so you ask for, okay, so I'll say.
Yeah, and I should say we should think of these morphisms really, they're just like a prototypical example. You could think of objects as just, you know, for example, sets, and then morphisms are just functions. So that's always kind of the paradigmatic example that one should have in the back, right? They satisfy all the properties you would want sets and functions to obey. Of course, they don't have to be sets and functions, but it's kind of modeled off that.
Yeah.
Yeah.
So, and in fact, one thing that you can do if you have, two functions where the, output of one matches the input of the other, you can compose them. And so actually, let me add this here. Let me put this right here. So I have objects and morphisms, and then together with the notion of composition, or like a composition rule. So I'll just say a rule for composing them. So in other words, if I have a morphism, or think of it as a function, an example from x to y, and then another one from y to z, call it g, then you ask that there be a third morphism that is, do f first and then follow it by g, or their composition. So of course, you learn how to do this with sets when you're like in middle school or something, whenever you learn about sets. I don't know, elementary school. Kindergarten. Okay, so with a way for composing them. And then you'd like some things to make sense. Like number one, you'd like composition to be associative. So if I have three of these things, it shouldn't matter which order I compose first. So I'll just say, okay, this data should satisfy a couple of conditions. So subject to two conditions, this stuff. So one, I'll say composition is associative. And then two, you ask that every object come with a special morphism called the identity morphism. So in other words, if you have a set, you can think of a function from that set to itself that just does nothing. You take an element in the set and you just send it to itself. It's a very boring function. But that function plays a special role in the land of sets, in the category of sets. It's like this, it kind of acts like an identity. So you ask that there exists a special morphism called the identity. So this is the identity. And what that means is it satisfies a certain property. So in other words, if I have an object X, what we're saying is that you would like a map from X to itself, which I'll call IDX, that says, and that it's true for any other object Y. There's one there for Y. So that means if I have a morphism from X to Y, call it F, well, this identity, it's characterized by the following idea. I can first map X to itself with the identity, and then map over to Y by F. So I can do IDX followed by F, and that should not change F in any way, kind of like the identity function. Or similarly, I can first apply F and then kind of stay put at Y. I can apply the identity on Y, and that shouldn't be any different than F either. So this is kind of what it means to have identity morphisms. You say there exists a special morphism in each object, call it ID sub, whatever the name of the object is, and it fits into this kind of string of equalities.
Yeah, maybe let's pause for a second, because maybe we've written a lot. So let's take a step back. So you've written a list of properties of axioms, right? And what I was implicitly saying earlier is that an example of a category, right, is that the category of sets, which we'll call, I guess we'll just call it, I don't know, capital S sets, like that. Okay, and in this category, the set of objects, well, the collection of objects, each element are sets, and then morphisms are functions between sets. Right, and right, and this satisfies those properties, because indeed, for any set, you always have the identity morphism, the identity function on that set, right? It's so for every for every x, identity of x is the map from x to x that sends little x to itself, right? Now, Okay, so maybe some people who haven't seen this before is, what's the point? Why are you formalizing something that we already know? Can you give us an example of a category where the identity map isn't what you think it is?
Sure. Okay, great. So I have actually two examples. I think these are two of my favorites for first introduction.
Okay.
Set is one. Okay, so after set. So here's one. I like linear algebra. Maybe machine learning people, they like linear algebra, right? Because it's all
that's a great example. Yep.
Good. Okay, so let's talk about matrices. So there is a category which I'm going to call mat sub R, and this stands for matrices. The objects in this category are natural numbers. So N, M, which I'll denote. I'm going to use those letters for natural numbers. So objects are natural numbers, let's say greater than 1, greater than or equal to 1. And what is a morphism from N to M? Well, it's going to be an M by N matrix. So I'll say a morphism between two natural numbers is an M by N matrix with entries in the real numbers. So, a morphism from 2 to 3 is a 3 by 2 matrix. So,
2 by 3 or 3, I guess.
It actually, you go the other way. Yeah, so this is a 3 by 2 matrix. So, whatever your favorite numbers are.
Oh, I guess, are you multiplying from left to right instead of from right to left?
Yes.
That's okay. Or
wait.
Yeah.
Let's see, because I want to compose them. So let's say I have another morphism from 3 to 4. This is a 4 by 3 matrix.
Oh, okay. So you are going from 3 by. Yeah, you're right. Sorry, I got my directions mixed up. Yep. Okay. Yeah.
So in fact, let me just give this a name. Like if this is, I don't know, A is 3 by 2 and B is 4 by 3. How do I take these two matrices and get a 4 by 2 matrix? Well, I multiply them together, and that's 4 by 2.
Right.
So in this case, in this example, objects are natural numbers, morphisms are matrices, and composition of morphisms is precisely matrix multiplication that we know and love. And then you just have to think, okay, is this associative? Yeah. But to your question though, what is the identity? What is an identity morphism?
Well, it has to be the identity matrix, right? What else could it be? Yeah.
Exactly. Yeah. So the identity IDN is precisely just the identity matrix. Yeah, because if I multiply by the matrix, whatever, it satisfies exactly the thing on the previous slide. So
yeah. Okay. I see why it's like the identity morphism will, I guess, always have to be an identity like object because of the property it satisfies, right? Because we know that here the whole point is that if let's just write down the defining property again. So if you have like a matrix, what am I going to call it? So if we go to this example, right, we need to make sure that A identity 2 is the same thing as identity 3A. And I should just say that this composition is sort of optional. It's just this is the composition sign, and you can omit it. I guess you've omitted it. I'll just put it just so like letters don't collide, and we have the distinct objects separated. But okay, it's optional. But anyways, so that was the defining property of this identity, right? So here's an identity 2, here's an identity 3, and so because of this property, the identity morphism has to be kind of identity-like. But strictly speaking, it's not the identity function because the object itself isn't a space. It's just a natural number, right? So in this case, the identity morphism isn't strictly speaking an identity function, right?
Correct.
But it is, in some ways, it is the identity function if you kind of do some further extrapolation, which isn't part of the definition itself. Just that if we think of the matrix as acting, if we think of this as acting on, acting on Rn, then it is the identity transformation. But that's strictly speaking not part of the categorical input, right?
That's correct. Yeah.
Right. Yeah. All right. Yeah. This is a great example, I think, of what what an example of a simple yet non-trivial category, and it sort of liberates you from thinking of the identity morphism as strictly speaking an identity map. It's only an analogy.
Right, and I like this example for another reason, which it relates to what you're saying. So in the kind of traditional or famous examples of categories like sets or groups or topological spaces, whatever, and those are all sets with additional structure. Like a group is a set together with a notion of multiplication. A topological space is a set together with a topology, blah, blah. But not all categories consist of sets with extra stuff on them.
Right.
And we have just seen this as an example. Our objects are not sets, they're numbers here.
That's right.
So, yeah.
That's great. You said you had another example. I'm curious what that other example is.
Yeah. So this is another warm-up example, which turns out to be super important. So it's like a good example for this.
Okay,
for this
let's do it.
Okay, so example, let me just write it here. So I'll just say it in words. So every preorder is a category or preordered set. If that's not familiar, maybe people have heard of posets or partially ordered sets. So let me just say, let me write this down. So a preorder is a set together with a binary relation that is reflexive and transitive. So this is what a preorder set is, and that relation is called a preorder. So with a reflexive, transitive, binary relation, okay, if this is like blah, 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 what I mean is that you have a set together with a way to compare elements in the set, usually say less than or equal to. And reflexive means that every element is comparable to itself, less than or equal to itself. And of course, transitive, okay, you know what that means. Oops, if I did write it properly. Okay, if x is less than or equal to y is less than or equal to z, then x is less than or equal to z.
Right.
So
let me just write that up. Yeah, so x less than y less than z. That implies that. Right. That's what transitive means. Yeah.
Yep. Okay. So claim every preordered set. Ordered set is a category. So the objects are just the elements in the set. Oops, in the preordered set, the elements I should give it a name. Every preordered set P. So objects are elements in P, and then a morphism, the morphisms from X to Y are just precisely this relation. So let me say it this way. I'm going to write it this way. If X and Y are elements in my preordered set, then remember we use this notation P of X comma Y to denote the set of morphisms from X to Y. So here's the point. This set consists of one arrow if X is less than or equal to Y and no arrows otherwise. So in this category, there is at most one arrow from X to Y. At most one morphism. So P of X comma Y is, I will just say, it's basically the 1 point set, which I'm denoting by an asterisk. It's isomorphic to the 1 point set. If X is less than or equal to Y, and it's the empty set otherwise. Like either you have this picture or this picture. Either X is related to Y or it's not. And that's what that's kind of capturing.
Oh, I like this example as well. Maybe I can already see that there's several interesting examples you can do here. So the first simplest example would be, let's just look at just the real number line, right? With the usual, the underlying poset itself is R with the usual inequality of less than or equal between two numbers, right? We know what it means for two numbers to be less than or equal to each other. And so one can just apply this definition to that,
Yeah.
right?
Mhm.
Well, do you want to say? I'll hand the baton to you. Like, what do you?
Oh no,
Yeah,
yeah, it's exactly correct.
yeah.
So then just to double check then, you need a notion of composition.
Mm-hmm.
But that's precisely this transitivity above. So let me
Mm-hmm.
just write this here. This is composition. If I have a way to go from X to Y and a way to go from Y to Z, then transitivity gives me a way to go from X to Z.
Yeah.
Mm-hmm. And then checking associativity is kind of like there's nothing to check. I mean, it's there.
Yeah. So let's just draw a picture because I kind of I think this is also illustrative something, right? If you just order, so like the real number line is very dense, but I'm going to draw it like as a discrete set because the topology it doesn't come in at all in this story. But if I just draw every real number as a point, then of course what's going to happen, and I draw it in their ordering, then what's going to happen is there's going to be an arrow between all these guys. Of course, like this is like 1, I don't know, this is pi, this is 10. I'm leaving out a bunch of things, but you're going to have those kinds of arrows. And so that's how you could sort of visualize this if you were to sort of draw it out in a line like that, right? And of course, there might be, okay, this might be 2, and then you'd have an arrow that goes this way. And yeah, that's how I guess you could draw. This is how people typically draw categories like this with these diagrams, right?
Yes, exactly. Pictures are very helpful.
Yeah.
For sure.
Yeah.
And then just to mention, here's the element 10, and there's an arrow that goes from 10 to itself, and that's just the fact that 10 is less than or equal to 10. So
that's
those
right.
are the identities too.
Yeah, and then actually we could even one-up this example with say R2, right? Pairs of real numbers, and then this could be, x1, x2 is less than or equal to y1. Okay, maybe I should have used x maybe just to make it usual notation. So x1, y1 is less than or equal to x2, y2, if and only if the usual coordinate-wise comparison, right? And then this is interesting because then you could have, it's not such a simple linear situation. So you could have, you'll have things like there will be an arrow from this to that, but if you have one that's like further along the x and but the opposite is further along the y, so maybe something like here. So if this is like the plane R2, then these guys don't have an arrow, right? Because this one, the x is for this one, the x is larger, and then for that one, the y is larger, so they're not comparable.
Right. Exactly. Yeah. So this is another example of a category where the objects are not just sets with extra structure. So I think it kind of depends on where you're coming from. If you are in pure math, maybe you think of categories in the traditional, topological spaces, groups, or whatever. I really like preorders actually as a nice intro to category theory because you're just dealing with familiar things, but viewing them in a new light.
Right.
So when you were like 2 and you learned that some numbers are bigger than others, you were really doing category.
Wow. Okay. I think that's a good way to sell it. Yeah. To kindergartners or whatever when they learn about inequality. That's great.
So there's another category. You can have variations on this. I mean, you can take, I like finite-dimensional vector spaces.
Sure, let's stick to that. Yeah.
Okay, so there's a category called f-vect. Well, people call it different things. I'll call it f-vect for finite-dimensional spaces, and that tells you what it is. Objects are finite-dimensional vector spaces over some field, over some field, let's say R. If we want to indicate real spaces, I'll put an R there. And morphisms, let's see, if I have 2 spaces V and W, a morphism between them is just a linear transformation or a linear map. okay, and then you check this in like undergrad class. If I have two linear transformations, another one from W to U, if I compose them, is their composition a linear transformation? And then you do this homework exercise and you say, yes, it is. Of course, there's the identity on V. One checks that that's the identity in the sense of category theory. I think this is kind of what I was saying earlier, when a category is like a context in which you're having a conversation. So if you're doing some math and you have two spaces, and you have a function from one to the other, but it's not linear, that's an indication that maybe you should try to find something else that would be better for that little piece of math, right? Like if you have two vector spaces and only a function between them that's not a linear transformation, it's not compatible with the linearity in both of your domain and codomain. Category theory is kind of nudging you. It's saying, hey, look for something else. That's not going to work. That's not really good math. So, I think I'm jumping the gun a little bit, but it's funny because like in grad school, you'll see these things called universal properties. So you have like a whole bunch of objects with arrows between them, and the arrows behave in such a way that you call this picture a commuting diagram. And typically, sometimes authors can be maybe not super precise. So some of the objects in this diagram will be like sets, and then others of them will be, a vector space. And then it's not clear what the arrow is. It's like, okay, I have an arrow that's going from a set to a vector space. What's happening here? This is not in any category, right? Like either you have two sets and a function, or you have two vector spaces and a linear map. But when things are kind of mixed, it's a little bit unclear. Oh, what context are we speaking in? What kind of category are you working in? So this kind of language helps you, I guess, have a little bit of clarity in your thinking, or it makes you think, hey, maybe something a little deeper is going on. Let me be more careful about what I'm working with. So maybe vector spaces, yeah.
Yeah, or maybe another takeaway from this, which is related to what you're saying, is that, how do I say, actually, I think people will probably relate to this point already in algebra, right? So in algebra, when you learn at some point that if you work in the world of real numbers, right, then you can't take the square root of -1, right? So for reals, there's this, that this is not a real number. But then you sort of enlarge your space, the complex numbers, so you have the square root of -1. Right? And I think what you're trying to get at is that, okay, so you have this category of vector spaces, right? And you have linear maps between them. And if you're in a situation where you don't have a linear map, well, you could just think about it in the larger space of the category of sets, which is where things are now actually living. There's sort of two sides of the same coin. At first, we said a lot of categories are just sort of special types of sets. So there's like the category of sets, and then there's f vect, which sits inside of it, and there's probably some fancy category theoretic notion for this inclusion. But I think it's pretty intuitive what this inclusion means. It just means that all the objects over here are also objects in here, and then the morphisms here are also morphisms here, but they just live in this restricted setting, right?
Yes.
On the left side.
Exactly. In fact, there is a fancy category theory way to understand this inclusion. This is called a functor. And in fact, the one that you have written is called a forgetful functor. So what you can do, you can take a vector space and you can just forget about the linear structure and just view all of the vectors as elements in a set. So you forget the vector space part and you just have a whole bunch of marbles called vectors, and that's a set. And similarly, if you have a linear transformation between two vector spaces, you just forget the linear structure there and you just have a function between sets. So that describes a way to go from a vector space to a set, which I don't know how to call it, f of v, where f is the capital letter for the word functor. And so I guess that's the next topic.
Yeah. This is a great segue. So let's talk about functors. Although actually, I just thought of like a very fruity example, like another, like this forgetful functor. I don't know why I kind of smiled a bit when you said that, because like math people, we have this cool vocabulary, and I haven't heard of forgetful functor in many years. And then when you said it, like, oh, that's such a cool word. It's like that we're talking about forgetful functor. But I was thinking like there's like, I don't know. like a very fruity example would be, there's like people, there's like, white people, black people, Asian people, and this is like the forgetful functor. We're all human beings,
Yeah.
I'm not sure how to write that, but I was like, yeah,
Yeah.
right. So like that's a forgetful functor, like the map from like different people, different races, different genders to like
Yeah.
humanity. We're all
Just
part of
people.
humanity. That's the loving message we have. That's a forgetful functor. Okay. Okay.
Right,
Okay. Anyways.
yeah, let's be more formal about it now.
Yeah,
right?
let's be
Like,
more
let's
formal.
not
Okay, all right.
Right, so essentially we just said a functor is a way to go from one category to another. And just that even tells you how it should be defined, right? What is a category? Well, it's got some objects and some arrows between them or relationships between them. So a functor, it assigns for every object over here, another object over here. And for every arrow, an arrow kind of over here. Okay, so that's it.
Sure, okay.
Not really. I mean, you want it to be compatible with
Sure.
composition and so forth. But,
Sure. Okay, yeah, let's start writing and see where we go. Yeah.
Yeah. So I'll say a functor f from a category C to another category D consists of the following. So you get an object, I'll call it f of x, in the target category D for every object in the source category C. And then moreover, you also get a morphism in D whenever you have a morphism, which I'll call F in C. Okay, so a functor sounds like the word function. Function, what's a function? You have two sets and like things over here go to things over there. A functor is like an upgraded version of that because your things now are not just objects, but they come with these arrows too. So you want to assign that as well.
Yeah, and now I think about it in this coding example that I brought earlier, right? Like a function maps an object to an object, right? And you could think of like a functor as like maybe like an API change, right? Because you have like all these objects in one language, one world, this category, I don't know, the category of, I don't know, Python or whatever. And then you have all these other objects and maps in some other language, and then the functor like maps between those two things.
Right, that's right. So it's a way to go from kind of one context or one setting to another.
Right.
But that's not it, because you would of course like this mapping to respect the structure that's there.
That's right.
Okay, so we also have, so we have to be a little more careful.
Yeah, and a good API change will also do that too. It won't break composition. Yeah, okay.
Great, exactly. Yeah. So in other words, speaking of composition, such that, okay, how do I write it? I'll just write it and then explain it. So, okay, whenever F and G are composable maps in C. So in other words, let me write it like this. Here's a little picture, F and G. So the idea is I have this kind of picture. This exists in C. And the idea is, well, in a category C, I know that I can compose these two arrows to get another one called G composed with F. So the idea is, I have this functor now. I want to take this thing in the blue squiggle and map it over into another category D. And there are two ways I can do that. One person might say, I will compose F and G and then map that over by the functor F.
That's this guy, right? You compose first and then you use capital F, right?
On the left-hand side. Or somebody else might say, well, I want to first take F and G individually, map them over, and then compose.
And that's the right-hand side, right?
And that's the right-hand side. And then in principle, these could be two different arrows. But if you have defined things in a way that should make sense, you want them to be equal. And so that's what this condition is asking.
Yeah, and people who are familiar with group theory, this looks exactly like the notion of what's called a homomorphism. Yeah.
Definitely. In fact, I mean, a group homomorphism is exactly a functor. when you view groups as categories in a special way.
I see. Yeah, I guess that's left as an exercise to the
as an exercise
to the viewer. Yeah. Okay, but that makes sense. Yeah.
Yeah.
Oh, I think I know. Yeah. Okay, I'll just say it very quickly. And but like basically, you can take a group. There's a category where it's just one element, and the morphisms are just the group elements because you could just keep composing them. Right? The group structure is the fact that you're a group means that the morphisms itself is a group, right? And now
Yes.
composition is just multiplication in the group, right?
That's right.
Yeah.
That's right. Exactly
That's right. Yeah.
So there's a different, I think this is actually a really great example. So just to be super explicit, there is a category where the objects are groups and arrows are group homomorphisms, but that's not what we're talking about now. What you just described is a single group is itself a category as well.
That's right. That's right.
And in that category, there's only one object. What's a morphism? A morphism is like an arrow from that object to itself, and you think of a group element as a morphism from this one object to itself.
Yeah, actually, since we're talking about this, let's just draw the picture just now that we've gone down this rabbit hole. So, but I think actually it's very nice. So you have a group G, right? And then now this is category. So okay, so you have a group G is a group. Right, it could be any group. It doesn't matter. Infinite,
like
non-abelian,
whatever.
Yeah,
the integers.
Yeah, sure. For example, yeah, we could do that. But it doesn't really matter. But that's acceptable. Yeah, and then the object is just a single element. Let's just call it star because it doesn't matter what it is. And then the morphisms from star to star. Well, there's only one collection of morphisms because there's only one object. It's just G itself, right? And then you could compose morphisms because you could just multiply elements in G. So composition. Right, it's the same thing as group multiplication. Right. Okay, so the picture is here's star, and then there's like G, I don't know, G1 and G2, and then you can just compose them for G2. It's just G2 times G1, right? Yep. And the point is, okay, so what we were talking about earlier in terms of this comment about homomorphisms is that you can think of a homomorphism as a functor from this category to itself, right?
Yes, or you can take another group H, also view it as,
fair enough, yeah.
Yeah, and,
that's right.
And you can look at a functor from G to H.
Yeah, so there's a group homomorphism from a group to itself, and there's a group homomorphism from two distinct groups. But yeah, so in general, it's a functor from these two categories associated to the groups.
Yes.
Yes.
Yes. Yes.
Great. Yes.
So yeah. So if one were to like write all of this out, which I just realized we haven't finished the full definition of a functor, but the point is that this kind of respecting of compositions that feels like homomorphism from algebra. The point is, in the case of groups, it is exactly that. A functor is a group homomorphism. But let me finish the definition of a functor.
Yeah, I
there's one more thing.
Yeah, one back to you. I realized. Okay. Yeah, I'll let you finish writing the last thing. Yeah, go ahead.
Yes. What's special about a group homomorphism is that it takes the identity element in one group to the identity of the other group. So you want that idea to kind of hold more generally. So if I have an object X, here it is. We said that every object has an identity morphism on it, and I can apply the functor to that identity morphism. But similarly, I can apply the functor to the object X itself and get a new object called f of X. And that thing also has an identity morphism called ID f of X. And the point is you'd like those two things to be equal to each other. And so that's the last condition of having a functor. Right.
And of course, for the homomorphism case, that's true because now let's go back to the slide on the groups. The next one, right? By definition, a group homomorphism has to respect the identity element, but the identity element is the identity morphism in this case, so that property holds. Yeah. Exactly.
So okay, great. We just saw an example of a functor.
Yeah, and this was a great example too. I'm actually I'm pleasantly this is. Good. Nice how cleanly this is working out.
So I mentioned earlier an example I really like of a category is a preordered set. So if I have two preordered sets, what is viewed as categories? What is a functor between them?
Sure.
So let's tease this out. So example, okay, a functor let me write it this way. I will call it little f. I don't know, who cares?
Well, let's do capital F. I think we should be consistent.
Oh,
Yeah,
we
because
can- okay.
little f will be like a morphism in a category, and capital F will be like a functor.
Very good.
Yeah,
okay, consistency. I like
yeah,
it.
let's do
Okay,
consistent. Yeah.
a functor between two preordered sets, okay, viewed as categories. Okay, what does this consist of? Let me just write this out loud. I mean, write this down and talk out loud as I draw pictures. Okay, so, I have an element x in P, and that gets sent to another element f of x in Q. And, similarly, maybe I have another element y in P. By the way, this is taking place in P. This is taking place in Q. And that gets sent over to its image f of y and q. And then, well, for every morphism from x to y, I want a morphism from f of x to f of y. But I mean, what does that mean? What is a morphism? Well, it's like this notion of less than or equal to. And so similarly, whenever x is less than or equal to y, we ask then that f of x would be less than or equal to f of y. Okay, but what is that though? I have a function between two sets that sort of preserves the ordering of this set. So i.e., if x is less than or equal to y, then f of x is less than or equal to f of y. And that's precisely just an order preserving function, or a monotone function, if you like.
Yep.
Order preserving function. And so I like this example because it kind of subsumes something that one might be familiar with. Earlier we said, oh, if you learn about, ordering of real numbers when you're a kid, you were doing category theory. Now, when you got to like elementary school and learned about order preserving functions, you were still doing category theory because you were dealing with functors.
Right. So as soon as you learned how to plot a function, if the function is not below the diagonal, that's a functor. Right?
Yes, exactly.
All right.
Exactly. Okay.
That's great.
So here's an example of, a new concept, maybe category theory, kind of subsuming an old or familiar idea. So I like this. Functors are really, between preordered sets, are just order preserving functions between them.
That's great. This is a great example. I like it.
The next example, I think it's important that we talk about Hom Functors.
Yeah. Okay. Let's do it. Okay.
So let me just kind of jump into it.
Okay. Okay. This is where things start to get a little meta, I would have to say.
They do start to get a little bit meta, but maybe we can think of down-to-earth examples along the way.
Meta in the sense of higher level, not in terms of the tech company. Just in case, I remember I was kind of upset when they named that. Like, man, because I like the word meta, and every time you say meta, you're gonna
I know.
like okay.
You have to have a disclaimer now. Yeah, not that meta, the other one.
I know exactly. I mean, I know that Google is also a number, but nobody uses that number, so it's okay.
Right. Yeah. That's fun.
Okay.
Okay. So the example I want to now give is something that's called a Hom Functor. Okay, so it goes like this. So suppose C is any category. It can be any of the favorite examples we've discussed so far, or just think of it generally. Okay, then every object in the category C defines a functor from C itself into the category of sets. And I want to describe that for you now. So every object, let's call it Z in C, defines a functor from C to set. And I am kind of bothered how I've written this, because really I gotta add this little bit of decoration called op, which I'm not gonna describe now. But if I don't write it down, it will bother me.
Sure. Okay. So, well, we will revisit that later.
We will revisit.
We need to. Yeah.
But just ignore it for now if you like, and just think I'm going to describe for you a functor from C into set. So in other words, I gotta describe for you a way to take something in C and to get a set from it, given the fact that I've already chosen an object in the category. Okay, before I write this down, think, what's a category? Well, it's a bunch of things and relationships between them. By a relationship, I mean an arrow or a morphism. So that's kind of all I have to work with. And that's going to come out of this definition right now. So how is this defined? Well, take any object, call it capital X, and I need to get a set out of it, okay? So I have a set Z, and now I have another set X, and given just these two objects, I don't know what I just said. I have an object Z and an object X. Given these two objects, I need to get a set from them. There's like only one thing you could do, because in the definition of a category, it's kind of like right there. I can look at the set of all morphisms from X to Z. So maybe I'll even write like Z in blue so that we remember it's the thing that was given to us. And then X is like the variable. Given as an object X, I get a set. This is, the set of all arrows from X to Z, all of them. Mm-hmm. Mm-hmm. Now, to define a functor, you have to also say how it behaves on morphisms. So I just described its action on objects, but what does this thing do on morphisms? Well, let me create a little bit more space for myself. Can I move this up?
Yep.
Yes. Okay, great. So this is going to be interesting. I have another object, Y, okay, and under this assignment, it goes to the set of all morphisms from Y into Z. But now the point is, given any morphism F, I need to describe a function between these two sets. Okay, now I'm going to put a question mark here because I've drawn this arrow going down, but I need to think about this.
I think you have, but since you have C up, actually the arrow is going to go the other way, right?
Exactly. So why is that? I mean, here's how I think of it. First of all, the question is, how is this arrow pointing in the wrong direction defined? And then once we see how it's defined, I think it'll be clear why that's the wrong direction.
Yeah, I should just comment, like, one of the beautiful things of category theory is its rigidity, right? Almost, yeah. And this is true of many things in mathematics, but especially so in category theory. Basically, you can correct, if you ever forget something or are unsure, you basically take a step back and ask, what's the only sensible thing to write? Right? Exactly. And that's what we're going to do live right now. Just like exactly. in the previous slide, it's like, well, there's only one distinguished morphism, which is the identity. So if you're going to map the identity to something, then it has to be that one, because that's the only thing that you can write in like sort of an agnostic way that isn't preferential to any idiosyncratic choices, right? Exactly. And the same thing's going to happen here. So it's like to go back to the coding analogy, it's like type checking or compiling your code. Like there's just only one way it's going to run correctly, and so we're like kind of compiling our definition right now.
Exactly. So this may be the first time we've ever seen this, and so we say, okay, given a morphism F from X to Y, my goodness, how do I get a function from these things on the right hand side, right? Okay. So what does this say? To get a function on this right hand side, well, if I have the arrow pointing down in this way, what that means is that for every arrow, let me call it G, that goes from X to Z, okay, so here's an arrow G from X to Z, I would need to get an arrow that goes from Y to Z, okay, so I will draw this here. Okay, so then the question is, given this thing, and then given this thing, is there a way I can combine them to get this like diagonal? And then the answer is like, I don't know, no. I mean, one might be tempted to reverse G and make it go in the other order, but we don't know if G is an isomorphism. We don't know if it's invertible. Okay, so that's like a little bit of type checking. That doesn't make sense. But if we go the other direction, it will make sense. So I claim that this direction is where we want to go. In other words, given a morphism from Y to Z, which I will still call G, okay. So given a morphism from Y to Z, can I get a morphism from X to Z? Yeah, now I can.
Right,
because they all line up.
Right, now you can just follow the arrows, unlike the previous case.
Exactly, now I can just follow the arrows. So this should be do F first and then do G. Mm-hmm. So in other words, this is called pre-composing with F. So I do F first and then I do G. So I pre-compose G with F, and that's denoted, I think this is F upper star.
Yeah, and if you're a geometer like me, I would just call it pullback.
Pullback, okay, yeah. Pullback along F, yes.
Yeah.
Exactly. So the point here, and this is the reason for that op above, is that a functor now kind of changed the direction of the arrows. So I had an arrow from X to Y, but when I mapped it over into the category of sets, the arrow goes from the image of Y to the image of X. Mm-hmm. So people call functors with this arrow reversing property. These are sometimes called contravariant functors. So you can either say, oh, I have a contravariant functor from C into set, or you can just omit the word contravariant and just write an op. The mm-hmm. op means opposite. Mm-hmm. It has to do with opposite categories, which might get too much into it, but this is kind of the idea.
That's right. So this, just to summarize, so a functor in this sense, which I guess would be by default, you have a covariant, right? It's the same thing as contravariant from C to set. Mm-hmm. Right? Those are equivalent. Yeah. Okay. Another way of saying is that either you can reverse the arrows in the category or reverse the arrows in the functor, and they're equivalent.
Yeah.
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 Yep. Another comment is if you had made so here what you did was you put this special object Z. So we isolated a special object Z, right? We picked one. So this is the Hom functor associated to Z. Mm-hmm. You put it in the right hand side, the target. If you had instead made it in the domain, then it would have been a covariant functor.
Correct. Mm-hmm. That's right. So if I had put Z, if I had switched Z and X, then we could have dealt away with the op. Mm-hmm. But I chose this for a reason because functors, so this is a special example of a functor from C-op into set. Mm-hmm. But in general, functors from C-op into set, they have a special name. They're called Presheafs. Presheafs. So
this is where it gets really fancy. Like I think, well, I would think, category theory is going to be a more standard term than the term Presheaf. Like category theory shouldn't scare a math PhD, but Presheaf might, That's what I'm trying to say, I know I'm getting a little nervous now when you say Presheaf.
Oh, no, don't get nervous.
No, I'm being a little facetious, but, I'm just saying okay.
Okay, so let me just write this down on the next slide then, just so we have the word down. So a functor from C op, any category C op into set. Let me write it this way, actually. A functor C op to set is called a presheaf. So it's not like a presheaf is a functor satisfying some properties. No, it's just a functor from C-op into set. So you might say, well, why don't we just call it a functor from C-op into set? And then, I don't know, I'm telling you it's called a presheaf.
Okay, cool. That's good. I think, we probably maybe don't want to say too much about why it's called a presheaf, because that's going to take us down a very complicated rabbit hole. Maybe one thing, because as we were sort of unfolding this notion of the Hom functor, we made this comment about it being meta. And so maybe just to unpack things further, like why is it meta? Because so we picked this object Z, right? We defined this Hom functor. So Z is fixed. I put a blank here to inform the user that it's this first argument here on the left that's like the variable input. But what it is it's sort of the objects themselves are the arrows, right? Because here's X and here's Z's, and so now the collection of arrows here are the individual objects. And then you have these collection of arrows, which are the objects. So these are now, so arrows are, sets of arrows or morphisms are objects. And then the arrows between arrows are now kind of the morphisms in this new thing, right? So like the morphisms in the, let's say, the image of Hom are, okay, I'll use arrows informally, arrows between arrows. F in the original category, that itself was an arrow, and this F gives you like an arrow between. This is like the okay, this is kind of a weird way to write it, but it's sort of like, this is this arrow is like the Hom blank of Z applied to F, right? It takes the F arrow in the original category, and it gives you a blue arrow between the collections of arrows. So that's why it's meta. It's like different, like there's like higher level arrows from previous arrows. Exactly. That's the sense in which this Hom functor is meta. So this is like meta, Yeah. That's what I meant by meta.
Yeah, and it gets even, we can go even deeper.
Oh yeah, because you can consider categories of categories, and then there's like
yeah, I mean, even look at this assignment right here. You went from Z to Hom of blank into Z. That itself is like an assignment, because Z lives in some category C, and then you might ask, well, this seems to kind of behave like an object. So where does this live? And then is this assignment, a functor? And the answer is yes. And this lives in the category of Presheafs, basically.
The category of Presheafs. Wow, we just even one-upped ourselves again.
Yeah, but this is an extremely important functor. Actually, it has a name. I mean, I'm getting ahead of myself, but this functor is called the Yoneda embedding, and that's an important part of the Yoneda lemma, which I guess we're getting to. So
yeah, well, this is the perfect place to get into the Yoneda lemma. Okay, at this point, the reader might ask, okay, like why? What was it about this Hom functor that is worth now? Because you could keep abstractifying endlessly with no fruitfulness to it, but clearly there must be something important. So maybe what's the reason why we're going to go down this rabbit hole before we do? Like why do we care about this? Yeah.
Okay, great. So Presheafs are nice. The Hom functors are especially nice versions of Presheafs. Because, okay, so we had this special object Z, and we had another object X, and we are looking at all of the ways you could go from X to Z. Now this is very abstract, but there's kind of like some intuition behind this. And in category theory, I've used this word several times, like an arrow is like a relationship. So when you have an arrow from X to Z, you're kind of inquiring, how does X relate to Z? Or you're kind of probing Z with the object X. Now, if that's weird, I mean, if that is like, what are you talking about? I mean, think of it like I have some space. I don't know, this is like a set. Maybe this is a set. Maybe Z is a set. I'm in the category of sets, and X is like a little singleton element. So what is a function from a one element set into some other set? Well, for every element in this one element set, I pick out a single element here in Z. So if this is F, I have F of the blob. Right. So when I am probing a set with a one element set, I'm just looking at the individual elements, kind of like you're looking at Z from the perspective of a singleton set, which is like just looking at the individual elements. But you can maybe be more creative. I mean, if you have a topological space like a torus, maybe Z is a torus, and maybe X is now a circle. Here's a circle. You could ask for a continuous function from the circle into the torus. So you're kind of now probing your torus with this circle-y type thing. how can it fit into my torus? I don't know, maybe you like stick it on the side here, maybe you have it going around this hole, maybe around this hole. There are different ways to do it. So you can kind of see, I mean, I'm hinting at like the study of topology.
Exactly.
Which is when you're probing spaces with a very particular shape, a circle or higher dimensional spheres. And that turns out to be very useful there. You can gather information about a space by looking at how different spaces relate to it. Maybe you probe it with a point, that's not very helpful. Maybe you probe it with a circle, that's more helpful. Now, it turns out that the Yoneda lemma tells you that this is very advantageous. You're not just doing stuff willy-nilly, but you're actually gathering a lot of information. So really what the Yoneda lemma is saying, everything you want to know about an object, basically up to isomorphism, like up to the things you care about, is captured in all of the ways you can like probe that object with other objects in the category. Or an object is determined up to isomorphism by how it relates in the category or how it looks from the perspective of everybody else in the category. The analogy I like to use is like people. I mean, we were talking about like the forgetful functor on humans earlier. So we can bring in people as another analogy now, but like you can learn a lot about someone by viewing how they interact with other people. Yes, you can also have them go to like 23andMe or whatever and look at you know, look at them at an internal anatomy kind of molecular perspective, and you can learn a lot about a person that way. But you can also see like who they hang out with or who's in their social network, things like this. And so the point is that you can do the same for mathematical objects, not just people. And the kind of climax is not only does that give you a lot of information, it basically gives you all of the information. So in other words, two objects are going to be the same, they're isomorphic, if and only if they look the same from the vantage point of all other objects in the category. And the way to formalize that is to precisely look at these representable functors. This is like all of the ways of looking at X or looking at
Yeah,
Z.
great. Let's pause for a second because there were a lot of nuggets there, and I want to say a few things. So let me just go back and in order. So right, in terms of probing with circles and points, this is basically the starting point of basically of the specific kind of topology known as algebraic topology. And I'll just write the words, and of course this is a whole topic of study once you take a course on it, but this is how you're going to get the homotopy groups and homology groups. Homotopy and homology groups. And actually, maybe this is good to mention because if I sense, and I might be wrong, but I think category theory was kind of motivated by the structure, right? Because if you think about it, what are these things? These are functors from topological spaces to groups or vector spaces, as the case may be, right? I'll just say groups to be more general. But yeah, is that historically accurate?
Yeah. So category theory has its origins, or was kind of birthed from questions in algebraic topology, I think in the 1940s. So it's not just like a cute example, it's like a really important example.
Yeah, basically once you start, how do I say it, since there are so many algebraic topological structures, right, different assignments, so basically you have all these spaces, then you have ways to assign structure to the spaces, namely certain groups or vector spaces. What I wrote here, some examples. And once you have this pattern that consistently emerges, then you start to take a step back, like what is the common underlying structure? Then you get a category, and then you start having maps between these structures, and that's where you get functors and then ultimately natural transformations. I think that's like really the birth of category theory, correct?
Right.
Yeah.
And especially with natural transformations and trying to make sense of those.
Right.
Exactly.
Yeah, and that's one thing. And then another thing, let me make sure, this is just to go on this human analogy. Basically what we're, this thing about, understanding something from probing it. I mean, basically what we're alluding to is that it's like a strictly behaviorist interpretation of human behavior, right? So in this human example, we're going to have this like behaviorist, okay, I'm not sure I'm selling it right, behaviorist perspective, which is you could understand completely an object understand an object completely by how it acts, by how it acts, or in this case, it's the target, maybe how it is acted upon, right? Because it's like, what are all the possible arrows that point to it? That's all the ways it can be acted upon. And an object is completely determined by all the ways it can kind of be acted upon in this sense.
Right? Exactly.
Yeah.
Exactly.
Yeah.
And in fact, it holds in the other direction too. I mean, the statement is still true actually if you put Z in the first argument, but then it's like less fun for me to think about.
Oh, I see. Okay, so either how you're acted upon or how you act. Okay, we're not going to make a distinction. Okay. Okay, cool. All right, but I think this is now okay. We've built up all this momentum and anticipation. I guess we could just get straight to the Yoneda. Oh, although maybe we need to talk about natural transformations.
Yeah, because the actual, so everything I just said now, we just talked about, I think is like pretty intuitive. The kind of funny thing is that when you see the Yoneda lemma for the first time, it does not involve any of the words that we just said. I mean, like the intuitive words, right?
Sure.
In fact, you might look at it and you're like, what even does this have to do with anything? And the statement, yes, it does involve natural transformations, so maybe we should talk about them. So here's the definition. Okay, let's say given two functors f and g, both going from C to D, a natural transformation from f to G, which I'll denote by this double arrow so that we can remember kind of like what the types of everything are. So what is it? Well, it consists of a collection of morphisms in C. So I'm going to denote this collection like this. So in other words, for every object X in C, I have a morphism from f of X to G of X. So I'm going to say like X ranges over all objects of C. So this is basically a natural transformation, is a bunch of arrows at each object X, where either you apply F or you apply G to that object. So you ask for a way to go from one to the other, but that has to fit in nicely with morphisms in the following way. Okay, such that, I hope we're okay with commuting diagrams, such that the following, it's hard to write in Tagasino, following diagram commutes. So, okay, so here's the idea. I have part of my natural transformation. These are called components of it. Okay, so that's part of the data that I wrote above for an object X. Maybe I have another object Y, so I have part of my natural transformation, the component, the Y component. So I go from F of Y to G of Y. But now, so this is taking place in D, this picture. But now in C, maybe I have a morphism from X to Y. So I can apply F to that, and I get a morphism from F of X to F of Y. Or I could have applied G to it. So I get a morphism from G of X to G of Y. And what you ask is that it doesn't matter how you travel in this square. Either I can apply eta of X first, or G of F, or I apply F of F and then eta of Y. And the idea is that you ask that those two things be equal. So if you have a collection of these morphisms that satisfy this property, you say your collection of morphisms is called a natural transformation.
Sure. Yeah, this is probably very scary for someone who hasn't seen it before. You know, we've seen this a lot, so we might we might overestimate or underestimate how complicated this is. Why don't we quickly dive into an example?
Yeah. I don't know. What's a good example?
Do you have one off the top of your head?
I mean, so usually I think it helps to think of cases when C is really simple. Mm-hmm. Just kind of like for picture's sake. So maybe, okay, I have two cases and I have two things in mind. Okay, so example, not a specific category, specific functor, but just still in the abstract, but suppose C, the category C, right? I have two functors, F and G from C to D. Suppose C is just like this little, we call this an indexing category. So suppose it's just got, 3 dots and some arrows between them like this. Okay, so a functor from this little category, it just assigns, it's like passing from syntax to semantics somehow. I have like the syntax, I have these objects and they relate in this way, and I'm just going to assign some meaning to them. If I were fast with my pen switching tool, I might, give these different colors and then maybe just say, okay, I assign this by F and I get like F of the blue thing. I get F of the green thing. I get F of the yellow thing. And then the arrows composition goes through.
All right, I can change the color while you're writing. Okay, go ahead.
Oh my gosh.
Oh, okay.
Okay. Okay. Now, the same thing for G. If I apply G, I also get a triangle. So what I have is like this. Okay, so in the category D, I kind of have these little triangle pictures. Maybe like this. This is like blue, green, yellow. Sorry, I didn't think about this beforehand. That's but okay. This is like F applied to the category, and then I have the same picture.
Or G now?
For G. And then the point is that a natural transformation assigns this little vertex to that one. It assigns this little vertex to that one, and it assigns the one in the back to the one in the back. So now I have this little prism shape thing.
I see.
And what you'd like to do is to have these four faces, the three faces of this triangular prism. You'd like them to commute, these the rectangles on the side and then on the bottom. So like the kind of the flow, if I go top, side, or side, bottom, that should be the same for this kind of front rectangle.
Let's make it something like very concrete, like, so like you have, this might be like not quite precise because I'm just making this up, but basically the dots could be people, the arrows could be transaction, F could be assignment of dollars, G could be an assignment of euros, and then the natural transformation is a change of currency. So, right? Because all the transactions in dollars map to transactions in euros all the same, right? It doesn't matter what currency you're using. So I think that's valid, right?
Great. That's great. I should remember that in the future.
let me just write it. Let me just write it down because I actually like it. I'll probably use it in the future. So
that's
F,
great.
Yeah. So let's see. So yeah, C is just the category. Right. C could be a category where objects are basically interaction graphs, right? So this is an object. This is a single object here, which is I'll just call it like interactions, right? So this is a single object. So an object is just like among people, right? So here's one object. Another object would be like four people, sending money in a circle or something like that, right? So that's just another object, right? So the objects are interactions among people, and then so that's what this category C. So C is this category, right? The objects are people. The morphisms are the interactions. Yeah. Because we hear about the arrows. Yeah. So the objects are people. Morphisms, I guess transactions.
Yeah. So we have a blue person, a green person, and
That's right. So that's C here, and then D. This is getting a little cluttered here. Let me erase that.
Oh, you can erase that.
Yeah. Okay. And then D, or same thing. You have, but now there's like people. People and then dollars, and then like people and euros, and the same thing. Morphisms are transactions. And then a natural transformation is a change of currency. I think that's valid. It's a
I
it's a
think that's
partic
great.
Yeah, it's a particularly simple one because kind of a change of currency is just like is a scaling factor at it does the same thing at every point. But okay, we want to keep things as simple and probable as possible for I think for that purpose, then this is a valid analogy.
Yeah. Okay, that's great. So if I have a blue person here, I can then exchange, currency,
Hmm.
and then, do a transaction with this yellow dot. Or I can first exchange, do an interaction keeping the same currency dollars,
Hmm.
but then with this other person, but then I can kind of change currencies. And the idea is that it should be the
Yeah,
same.
exactly.
Fantastic.
All
That was
right.
fantastic.
I love this. Yeah, we're at the
That's
financial,
great.
getting some
Okay.
financial sense to our category theory, right?
Yeah, good,
Everybody
good,
likes
good.
that. Okay, awesome. All right, I think this fits the bill for what a natural transformation is. All right, all right. Math on the fly. All right.
So the definition of a natural transformation, you have these arrows, these eta sub x. Now, if each arrow here is an isomorphism, then you call your natural transformation a natural isomorphism.
Sure.
And that will be helpful.
Yeah.
So maybe I'll just write this down.
Sure.
If each, and maybe we should say what an isomorphism is. If each of these arrows is an isomorphism, then we call eta a natural iso, not just a natural transformation. So it's a special kind of natural transformation. Let me just kind of sketch the picture. So in any category C, I have objects X and Y. So a morphism from F from X to Y is called an isomorphism if there exists another morphism in the other direction, call it G from Y to X, so that if you compose them in any order, you get the identity. i.e., if I apply F first and then G, that should just be the identity on X. Or if I apply G and then F, that should just be the identity on Y. Now, if you have a morphism F that has another morphism G that satisfies these two things, then you say F is an isomorphism. The nice thing is that if your category is like one of these famous ones, then an isomorphism is like a familiar notion. So in the category of sets, isomorphisms are set bijections. In the category vector spaces, isomorphisms are linear isomorphisms. Right. Similarly for group theory. So this just kind of generalizes this definition that we kind of learn in different math classes, and in math undergrad. They have different names there, but now they're kind of subsumed by this one notion.
Actually, this is great. We probably should have talked about isomorphism sooner, but the thing is that the word isomorphism is this generic property, which is summarized by these statements here. And it's just that the different notions of isomorphism just happen in different categories, which is why they have a different flavor, like group isomorphism, vector space isomorphism. But one of the selling points of category, the feature of category, is that you don't have to worry about the particular instantiations of the isomorphism. It's this bird's eye view of this is what an isomorphism abstractly is in any category. And then these particular categories are just instantiations of those particular properties.
Exactly right. So given that if you have a natural transformation, these kind of red arrows in our prism, if each of those were isomorphisms, I don't know what that would mean in our people example.
Yeah, I don't know what that, it's like, what would that mean if in our people example? So maybe maybe the currency one's going to make the most sense because I don't know but it would be, like if I interacted with you and you enter, there's a map back where I have the same amount of money. So it's like net, like I can get back the amount of money after our two interactions, basically, right? Yeah.
Something like that.
Yeah.
I mean, it should also, not every two functors have an isomorphism between them. So it's also fine if we can't think of one. Yeah. But that's important because the Yoneda lemma makes a statement about functors being kind of isomorphic. So maybe we'll revisit this idea a little bit later. But now that we know what natural transformations are, maybe I can actually say what the lemma is. And
yeah. Let's state the lemma. Yeah. I don't know if we'll have like a shot at proving it, but let's at least state it and see how we do. Yeah. Okay.
Yeah.
Okay. Let's do it. Let's do it. Okay.
Okay. So here we go. Okay, theorem.
/ lemma.
Yeah, Yoneda Lemma. Okay, so we have a category C. Now, here's the statement. For every object X in a category C, and every Presheaf, or let me just say every functor, capital F, C up into set, there is a bijection of sets. So we just said a bijection is an isomorphism of sets. So there is a bijection of sets. So well, on this slide right now, there's only one set that like immediately comes to mind, and that's just take F and apply it to X. Okay, I have an object, I have a Presheaf, I can apply the Presheaf to the object. So I have a set, F of X, this is a set. This is a set. Okay, and the Yoneda lemma says that this set is in one-to-one correspondence with another set. And that set is the set of all natural transformations from some functor into F, or from some functor to F. So I'm going to denote that set. Let me write it like this. I'm going to introduce new notation. So nat means the set of all natural transformations from some functor, which I'll say in a second, to F. So now I got to tell you what goes in the blank. So I need a natural transformation from something to F, and it's going to be our beloved Hom Functor. So the functor that takes an object blank and looks at maps into X. So this is a functor, this is a functor. So I can look at natural transformations, not just one, but all of them. So this theorem says that the set, so this is a set, let me write it, set of all natural transformations from this functor, this Presheaf, sometimes called a representable, at X to F. So the set of all ways to go from C of blank comma X into F. So the statement says for every one of these natural transformations, there is a particular element in F of X, and then vice versa. So they're in one-to-one correspondence. That's the theorem.
Wow. Actually, okay, let's just pause here for a second. I remember thinking of a good example, but I think I had X on the other side. Do you have a good example of how to think about the Yoneda lemma?
Well, I think the example I like to have in mind is when you choose F to be a particular functor. And in fact, when you do that, you get a corollary to this theorem. And the corollary is that kind of behavioral idea we were talking about earlier.
I see.
And that's where the intuition is. Not quite on this slide, but when you choose F to be a certain thing, you get this nice result.
Before we move on, actually, I thought, as I was preparing for our conversation, I thought this is, I was playing around with different choices of F just to get a concrete feel of this, because this is so abstract, even for a math PhD, if you if you don't think about this all the time. And I feel like this is one of the things where if you don't think about the Yoneda lemma for a month or two, maybe you'll like forget what it means, like, you know. So here's a very simple example, which I think is really nice. So actually, what I'm going to do is switch the roles of X. So you like to put X as the target. I'm going to put X as the source. So let's do an example. The Yoneda lemma. So we want to look at natural transformations from Hom of x into blank. So I'll put x as the source rather than the target. Okay. Into so let's f this functor that's the target of this natural transformation. Let it be the identity functor. So it's the functor that does nothing. Every object gets returned. Every morphism gets returned. Right. So I'll write this as natural transformations to identity. Okay. So the claim is that this should be in one-to-one correspondence with f of x, which is x, because again, f is the identity functor. Mm-hmm. What is this actually saying? Okay, so if we write out what a natural transformation should be doing, then so I guess our variable object can be called z. I guess maybe so pick any z in our category C, right? So then what do we have here? Then we have Hom of x into z. That's the, let me use colors here. So that's this functor here. And then we have this functor, identity applied to z is just z. Okay. And if we have another object, call it y. Right, so there's a Hom x and y here. Okay, and of course we have arrows between z and y, let's say, then an f. So we have an f here, and then since it's the identity map, it's still the same f here. Okay, so we need to define a natural transformation. So what is this, right? So we have two functors, right? Green, we apply the identity functor to the arrow between z and y. We get back the arrow between z and y. Upstairs, we get these two, we get the induced f by abusive notation. We still write f between the two Hom objects. How do we evaluate, how do we just construct a natural transformation, right? We're trying to construct this vertical map. And here's the thing. Now you ask yourself, what's the only way I could take a Hom from x to z and get a z, go to z? What I should do is just pick an element of x, right? Homs, this Hom thing here, what is this red thing? That's just the space of all arrows from x to z. And now you're asking, now you're asking if I have, let's use a different letter. So an alpha in here. So let's say alpha is an element of this space. So alpha is a map from x to z. I need to get an element of z from this alpha, which is an x to z. How do I do that? I just pick an element of x and evaluate on alpha. So to get this map, I can go alpha goes to alpha x, sum x and capital X. And likewise, if I have some beta in here, then this goes to beta of x. And if beta, and of course this diagram commutes because it's just evaluation, right? Either I can go down the first path and just evaluate alpha at x and apply f, or if beta is really the composition, right? So if beta was the composition of, what am I trying to say here? Yeah, if beta is really f of alpha, then because that's what it means for f to be on the upstairs, then the vertical, when I go downstairs, this commutes as well. Okay, this is getting a little maybe confusing, but if you stare at this long enough, what you'll see is that what I'm trying to say is the only natural way, that's why it's called natural transformation, to map a function to a element in the codomain is to take an element in the domain and evaluate that function. Okay, that's the long story short. Yeah.
Right. Yeah.
Yeah.
Which is one of these nice perks of category theory. You kind of feel like there's only one thing to do, and then that turns out to be the thing.
Yeah. So let me write it in words because it's hard enough to think about this, but to talk about it when you're writing it, I realized that, me doing this for the first time, I was kind of struggling, so I'll spare myself the further embarrassment. But what I'm trying to say is what this is saying is that, I'll write it in words, let me take a different color. The only natural way to map a function to an element in the codomain, that is the range, is to pick an element, or let's say it more succinctly, to evaluate on an element in the domain. Okay, and it's this choice of element in the domain, right? Because x is fixed here. That's what this Yoneda embedding is saying. It's saying the only natural isomorphisms from Hom x to blank and the identity is the choice of a little x in big X that does the evaluation, right? So every evaluation map gives you a natural transformation. So I'll say it even more succinctly. Evaluation, I'll call it evaluation of sub x, is natural transformation. And it's all the different choices of little x in big X that gives you those natural transformations.
Yeah, exactly. So maybe even going down here on the lower left-hand side, when you have fixed one of these little, maybe even write x naught, if you fix a little element x naught in big X, and then you look down here and you say, okay, given one of these maps from X to Z, how do I get an element of Z? Well, you have a lot of choices. You could have chosen anything in the set X, right? When you write some here. But the point is you don't. You only have one. It's the one that you chose to begin with in this kind of.
That's right. Because if you write enough diagrams, you'll see that you can't vary X willy-nilly. Like once you pick that X, you're stuck with it, right. Because all these diagrams have to commute. Yeah.
And that tells you where to evaluate. Yeah, exactly.
Yeah, in some sense, the proof of the Yoneda lemma is captured in this example. If you know it for one kind of example like this, you know it for all, because they all follow the same logic. It's like you need some diagram to commute, and then at some point you're just stuck, and then that stuckness just tells you what choice you had to make. You were forced. Yeah.
Right, exactly. No, this was a great example. Thank you for bringing it up.
Okay, I'm surprised how simple it is. This should be like on the Wikipedia page. Maybe I'll have to update it, but it's like a really good example. Okay. Anyways, okay, so we have an example of the Yoneda lemma at least, and it's really nice. Of course it's one of those. I feel like the Yoneda lemma is just something like you just need to like stare at a lot, and then it's easier to internalize once you pass the threshold. It's always harder to like recapitulate externally. But you were okay. So you were going to get to a very specific example, which motivates eventually some ideas about word use, semantics, syntax. Maybe let's get to that example, which is pretty canonical, but it's let's get there.
Have you ever thought about the analogy between this statement and the lemma and linear algebra? Do you see linear algebra on this slide? I mean, does something smell familiar to you here by any chance?
Let me think 1 second. No, not off the top of my head.
So when I think about this Yoneda lemma, there's a sense in which I think about vectors, and if I have a basis for a vector space, every vector is like uniquely, this linear combination of basis vectors. And if you think about it, this functor f from Ciot to set, it's like a vector. I mean, what's a vector? A vector is a function from, let's think in a finite dimensional vector space. It's a function from a finite set into the reals, let's say. Like if x is comprised of 3 elements A, B, C, a function is just a choice of 3 numbers. Like, pi, 10, and 2. That's a vector. So functions from sets into the reals, those are vectors. Now, if I have one of these vectors, maybe I'll call it little v. And, if I have like standard basis vectors in, let's say, R3, E1, E2, E3, my standard basis vectors, then every vector is this linear combination. I have some coefficients, and then I have these basis vectors, where the coefficients are exactly just if I'm in R3, this is just like the dot product of my vector against the ith basis vector. So this vi is equal to the dot product or inner product between v and ei. This is like exactly what this is saying. You know, I have some vector or some functor and I'm looking at its ith component or its x component. And what is that? Well, that's just like this pairing between a basis vector, which is like this representable. I kind of think of representables as like basis. They're like, okay, there's a theorem that says every presheaf is like, it's like built up from these Hom Functors. There's a theorem, they're like a co-limit of these representables.
Oh,
anyway,
I see.
So you pair your functor against these kind of basic functors, or you pair your vector against these basis vectors, you get something. In the case of linear algebra, we get a number. In the case of category theory, you get a set. But the idea is kind of the same. You have this functor and you can kind of say what it is component-wise.
I like it. I like it.
So yeah, that's kind of like the
That is really cool. This well, you know, this is already getting into the Brockett notation. It makes sense why you're at Sandbox AQ now, right?
Yes.
Nice,
Yes.
nice. Okay.
Yes. Okay, so anyway, I just think that's kind of helpful if you're familiar with
no,
linear
that's
algebra.
nice.
Now you can, yeah.
No, this is very beautiful because with that intuition, it's like if I forget how to write the Yoneda Lemma, I just think of this linear algebra thing, and I could probably remember how to write it. It's very powerful. Yeah, I like this analogy.
So presheaves are like vectors. I kind of think of them that way.
I like it. Okay.
So here's the climax. Okay, the climax is basically what we already said, but how do you go from this very abstract Yoneda lemma to this feeling of, oh, objects are the same, you know, up to isomorphism if they have the same context? So it's because of a corollary to the Yoneda lemma, which says the following. So basically says objects X and Y in a category are isomorphic if and only if their Hom functors are naturally isomorphic, i.e. if and only if C blank into X is isomorphic to C blank into Y. So remember, C blank into X, this is a functor. This is a functor. So what does it mean to say two functors are isomorphic? It means there exists a natural isomorphism from them. So,
and then in your linear algebra analogy, this is basically saying two vectors are isomorphic if and only if they act the same as dual vectors on the dual space, essentially, right?
Yeah. Or I think.
Yeah, like two cats are the same if only if their bras are the same. Right?
Right. Yeah. Or if you like plug in stuff for the blanks, like two vectors are isomorphic are the same if they're the same component wise, like entry wise, if you plug in stuff.
Yeah. So I'll just read what I said just right. So like, you know, like in QM linear algebra, you would just say X equal to Y if and only if, like I said, right, two cats are equal if and only if their bras are equal.
This maybe doesn't look like the Yoneda lemma yet. So let me just kind of sketch this in words. And we don't have to go into a lot of detail, but I just want to kind of tie all of this together. What does this have to do with the Yoneda lemma? Like, how do you get from that to this? Okay, first, let me just say one direction of this if and only if is kind of straightforward. And it's if X and Y are isomorphic, then their representable functors are going to be isomorphic, or their Hom functors. That is because the passage, we mentioned this briefly earlier, but the passage from X to C blank of X, this is actually a functor itself. So it goes from the category C to the category of presheaves on C. So we kind of didn't get into that, but there is a category whose objects are presheaves and whose morphisms are natural transformations. That thing has a name. If people have seen it, it's called set up or COP, which is again like linear algebra. Presheaves are like vectors, and you know it looks like this.
Yeah, just maybe a comment. People have noticed, you know, sort of in set theory notation, X, Y is set of functions from Y to X. This is the category version of that, where now this is the set of functors from the upstairs object to the downstairs object. Yeah.
Yes,
Exactly.
exactly.
Analogous. Yeah.
Exactly. Perfect.
Mm-hmm.
Yep.
Yep.
Now, the reason I mentioned that is because this is an exercise you can do, which is that functors preserve isomorphisms. So if you know what a functor is and you know what an isomorphism is, you can prove, it's easy, that if two things are isomorphic over here and then you apply a functor, they're going to remain isomorphic, or their images will remain isomorphic.
Mm-hmm.
So this kind of forward direction follows from that. If x and y are isomorphic, then you can kind of conclude their Hom functors will be isomorphic because that passage was a functor. The other direction requires more thought, and I'll just say the other direction is given to you by the Yoneda lemma.
Okay.
So in other words, if I know that Hom into x and Hom into y are naturally isomorphic functors, can I prove that x and y are isomorphic objects?
Mm-hmm.
So now you can think about this a little bit. It has to do with properties of this functor, which I mentioned earlier. It's called the Yoneda embedding.
Mm-hmm.
But you can essentially show that this functor is what's called fully faithful. It has this kind of nice property, which then when you kind of try to go in the other direction in this corollary, kind of stare at the paper and you try to work it out and construct the isomorphism, and it's like the only thing that could possibly happen.
Actually, let's just say, because off the top of my head, I don't know it. I'll have to work it out, but maybe we could do it right now. Right. So I wanted to just unpack that just so we could do at least a little bit of homework on this. So we said that you'll have to help me out. So I think it was like natural transformations from Hom blank into x of f was isomorphic to f of x. But now let's let f, so that was, this was Yoneda. And the point is, now let f be itself another Hom functor, but with a different object, right? And then what you'll have is that you will have this statement. It's isomorphic. So f now, when I apply x, I put x in the first blank slot, and now it's Hom x, y, right? And my question to you is how does that inform what we just wrote? Unfortunately, we don't have the previous slide, but okay, let's just maybe just rewrite again. Yeah, so yeah, okay, let's just stare at this. What's the takeaway? Or how do we conclude that x and y are isomorphic?
Right. So let me think for a second. So
I think I could actually see. I think I could see. This sort of makes sense, right? Because it's basically saying all the Okay, here's where it makes sense. Because so these guys are now elements of. These are elements of set C op, and natural transformations are just morphisms in this category, right? So this is a category. Let's scripty C. This is itself a category, right? Its morphisms are natural transformation. Well, at least is this right? Yeah, that's right, because this is a functor category, so morphisms are natural transformations. And it's basically saying that the morphisms in this category are the same as the morphisms in C, right? So it's sort of like basically saying, yeah, the morphisms, so this is basically saying morphisms in C are like morphisms in the original C. Right, and so in that sense, like the when you said fully faithful, that's exactly what this is saying.
Right.
And I guess the hard part is, or the trickier part is, like, if it's fully faithful, then the underlying objects are isomorphic. But I think that sort of makes sense because if all morphism sets are the same, then when you start playing around with like inverses and composition, things just rigidify and you can't do anything else, right?
Right.
Yeah.
Yeah.
So that's the exercise. I believe it. Yeah. But it's like okay. It's just once you have enough experience and intuition as a mathematician. You just like, you know what to believe, so I believe it. But you know, you have to like sit down and write it out. But it's going to be more pain than it is worth right now. But I believe it now. Yeah.
Yeah. No, that's a great point. And so the idea then is that once you believe all this stuff, the intuition is that X, the object X, you can just basically think of it as its representable functor. Right? And like the relationships between X, as you're saying, the morphisms in C, you can basically think of them as like morphisms or relationships between the representable functors. So that intuition you're describing, you're just essentially thinking of X as like the way, you know, the totality of ways that all things probe it or something.
Right.
And that's that context idea that we were talking about earlier.
Yeah. So actually, this maybe okay. So yeah, maybe this is a good point to highlight. Okay. So the right hand side, maybe yeah. The right hand. I'm trying to extract from this like a pithy statement. Maybe you're more equipped to do this. Can you fill in the pithy statement from this, like in terms of like a word is defined by the company it keeps or something else?
So that's the corollary. Okay, so back to the corollary. The corollary was, so X is isomorphic to Y if and only if their representables are I can't get my C's in parentheses correct. If and only if they're representables. So this, okay, X is like a word, I mean, in this analogy. And C of blank into X is like.
By the way, when you write C, I think you meant Hom, or are you using abusive notation?
So C is my Hom. Yeah. When I write C of blank, I mean Hom. Yeah.
I see. I think it was because C. Oh, I see. Because C of X, Y was the set of morphisms between X and Y. But if you leave it blank, you're thinking of it as Hom. Is that right?
That's right.
That's right. I see. Okay, maybe I missed that, but I see.
I should have said that like 40 minutes ago. I'm so sorry.
Okay, maybe I might have missed that, but I was just like, I thought that might have been confusing. Okay, but
C of blank X. This is, I mean, Hom. You know, a blank X.
I see. Just for this slide, we could just pick Hom or C. I don't know. The isomorphism right now is.
I see what you're saying.
Yeah.
Okay, so I'll just use C because that's what I see.
Oh, okay, got it. Okay.
Okay, and it's true actually. If you go in the other direction. The kind of whether you go into X or out of X, it's
of course okay. Yeah everything's up to, you could just opposite everything and it'll be
there's this duality, right?
Right.
So here's the thing. So we've been saying this phrase, so this is by a linguist, John Firth. You shall know a word by the company it keeps. So I think when I think of this quote, I always think of the Yoneda Lemma, because you're kind of saying, okay, here I have some word like, I don't know, dog, which is X. And I'm like, okay, what's the meaning of this word? What is the meaning of dog? You know, you can say, oh, if I cut the leg off a dog and it has 3 legs, is it still a dog? Like, what if it can't bark anymore? Is it still a dog? Okay, so what's a dog? Well, according to this quote by John Firth, at least at the word level, you shall know word by the company keeps. Oh, like, what's a dog? Well, it's like this thing that appears in other sentences like park and run and ball and fur and whatever. Okay, so if I kind of think of language as a category, okay? So the objects now are expressions in my language. I have a dog. I went to the grocery store. Blue chicken. These are objects in my category. And a morphism, a relationship, one way you can think of this is just say there is an arrow from one expression to the other if the former is contained in the latter. So like, I went to the store is contained in, I went to the store to buy milk. So there's an arrow from the previous to the former. But there's no arrow from like ice to birthday party, because ice is not contained in the phrase birthday party. So that's your category.
So I guess the category is like a substring category, right?
Yes.
Just write that.
Yes.
Yeah. Okay.
Yes.
Right.
Yep. So your objects are strings, and then morphisms indicate substring containment. Exactly.
Okay,
so if I think of this C of X comma blank, these are like, this is kind of picking up all of the expressions that X sits inside. i.e., it's telling me the company that X keeps. So this corollary to the Yoneda lemma, if I have this kind of very loose, informal, intuitive perspective of it, like how do I know when two words are the same, X and Y? Well, the Yoneda lemma in that spirit says, well, they're the same if they have the same, if they keep the same company, if they have the same context, if they fit in the language in the same way.
Yeah. So okay. Let's see. So for people who are going to actually work that out for themselves, right? So if the category is this, so maybe I'll just write it because we just said it, we didn't write it down. So sort of, I guess the category of so objects are strings. Morphism is inclusion of strings, right? So as we discussed, and as one can work out, if you work with this category and think about it, you're not going to get something too deep, right? Like a word is equal to another word if it's the same word or something like that, right?
Yeah.
So there's something more going on eventually, I guess.
That's right. I mean, you can see why. Okay, first of all, let's just mention that this is, so i.e. language is a pre-ordered set.
Yeah.
In other words, if I have, two expressions like dog and, I don't know, some other one, either it fits in that expression or it doesn't.
Yeah. So like dog and like dog barks, right?
Yeah. So, dog barks. Okay, fine. There's an arrow there, but there's no arrow from dog to ice cream.
Right.
This does not exist. Okay. So what that means is that the image, so if this is the word X, if X is the word dog, this functor, when you insert another word here, you're going to get a set. And that set will either contain one element or none.
Right.
It contains one arrow if dog fits in that expression or not.
Right.
So if you look then at this isomorphism, it says that two words like dog and another word, I don't know, what's another word?
Cat.
Okay. Dog and cat are going to be isomorphic in a preorder. What does it mean to be isomorphic in a preorder? Basically, it means that they're the same. Okay. So dog is going to be equal to cat if and only if every expression that dog sits in, cat also sits in. Like these sets are simultaneously the 1 point set or simultaneously the empty set.
Right. Although that's like not like that deep of a statement, right? It's just basically saying two strings are the same if the whole tree of strings that you can build downstream from that are the same, which is like pretty obvious, right? So yeah. So
and that's not going to happen obviously in real life either. I mean, all of the sentences that dog sits in, cat is not also going to sit in. I mean, if you wanted this to make sense, in other words, you don't want to come to the conclusion that dog and cats are equal or something.
Oh yeah, I know. I was just saying, but this will give you the right thing, but it gives you the right thing in for like almost like in a tautologous sense.
Yes.
That's what I'm saying. Yeah. So it's correct, but sort of you didn't need to build category theory to know why dog is not equal to cat in this sense. Yeah. So okay. So how do I say? I'm wondering if we can. Okay. So we've talked about the Yoneda lemma. We've talked about this corollary, which is this. Two objects are isomorphic if and only if they're representable or their corresponding Hom Functors were isomorphic. This statement about language can be reformulated, although it's not particularly deep if you unpack the actual category-theoretic mathematics. It's just saying two words are the same, essentially, if they're the same string. But I think the point is, so just for context, you wrote a paper with your advisor and another co-author, I believe, right?
Yes, was published.
Yeah. And you explore these ideas much further in a way that's not as simple as it is here. Can you say something about that? And also, does this statement we have here about you shall know a word by the company it keeps, is that paper a much more powerful realization or manifestation of this principle? Can you say more about that?
Yeah. So I'm happy to say something about that. So the paper you are referring to uses category theoretical ideas, yes, to kind of explore mathematical structure in language, motivated a little bit by this saying, "You shall know whereby the company it keeps," but I think actually that sentence is not all that there is. I mean, that expression is not all that there is. In other words, maybe we should refine John Firth's quote a little bit. And the reason I'm suggesting this, and the reason that we kind of wrote the paper and motivation behind it, is basically in this world of NLP that you're mentioning, and especially the success of large language models. And so what's very interesting about that is that you can, train one of these large language models to generate coherent text, right? It's like indistinguishable from human text, more or less. And what is that model trained on? You don't have to tell it what nouns are and what verbs are, etc. You just kind of give it all of this unstructured text data. And what does that mean? Well, you have what goes with what, right? Like you have all of the sentences, in their data set. So you know what kind of things go with the word dog because you train on a whole bunch of correct English sentences. Maybe it's got some dogs in there, maybe some ice cream trucks, I don't know, whatever, a whole bunch of English things. But in addition to that, once you have like a sample of correct English text, you get these frequency counts. Like, oh, dog occurs quite often with like park. You get things like, well, gosh, like the word red does not appear often in front of the word idea. Like just to borrow from Noam Chomsky, like red idea is not a thing really. And because you won't find it, the probability of that expression is very low. So we were just wondering, like the question was from a mathematical perspective, what is the structure that is inherent in just unstructured text data? Like you just have a whole bunch of words. What's the math there? So kind of asking what's going on under the hood of large language models, not like, what do the weights mean in the neural network and the attention mechanism, but just from a more abstract mathematical perspective. If your ingredients are strings together with statistics or probabilities attached to those strings, what can you do? Apparently a lot, because hello, look at AI. So like apparently a lot. And we just wanted to know what is that? Like how much can you say? And what is a good framework for exploring those ideas? Where do you even start? So this kind of Yoneda lemma hints that category theory could be a good place to start to kind of understand such a framework or to present such a framework. So that's what the paper is about. I mean, I like this quote by John Firth, "You shall know word by the company it keeps," but it's not quite everything, because you also need these statistics. It's not just what goes with what, but it's like how often or the probability of those things, because that's what large language models have access to, and then they do well on that. So the question is, like, how do you describe the mathematics potentially of that?
So maybe this is a good place to kind of wrap this up, and I want to just write the ideas down because we don't have time to kind of unpack that. So just to unpack this, so people will know in the ML space that basically what these large language models are doing are doing these conditional probabilities, right? What's the probability of x given y? So here's y is like the previous context, and x is basically the next word. So like y could be like, I'm going to walk and it's much more likely to be dog than ice cream, for example, right? So anyways, maybe you could just sketch out and just like write the buzzwords or the concepts. Okay, so we have this category of substrings. It's a partially ordered set. You have the Yoneda embedding, which basically captures how words are used inside other expressions just by inclusion. And so in my reading of your paper, basically there's a way to, literally enrich. It's actually a technical term, but you're going to enrich your category to have additional structure. In particular, you're going to have it for these, now arrows are going to actually become enriched with these probability distributions numbers, right? Exactly. So you're going to enrich to get probability distributions Right, and they happen over the morphisms because you only have these probability distributions when there's a substring, right? And that's what morphism is, right? And so from there, okay, maybe this is where you can take it away. You get more stuff, more bang for your buck, in that now what was just statistics meaning these numbers, you can kind of interpret semantics. Now that's the part where I maybe you can sell that, because I'm not quite sure what the distinction between semantics and syntax is. Actually, can you maybe explain that a little bit?
Sure. So the idea is quite simple. You have this category of strings where morphisms are given by substring containment, and I'm going to call it L for language, but we can call it whatever. And then, yes, the idea here is that, like, I'm going to use, I can use the word dog, or actually, I like colors. Okay, so if I have a word like red and another word like red rose, then there's an arrow there. But as we were saying, just knowing that those two things go together is not that helpful, because there's nothing stopping me from concatenating red and idea, right? So in some sense, yeah, maybe there's an arrow there because I just spoke that phrase, but there's not a lot of meaning to it, or the frequency that these expressions occur in natural language contributes something to their meaning. Like if I say, oh, I woke up and had the best red idea, you're like, that's strange. I wasn't expecting that. Okay, so you want to kind of capture that. So the idea, as you were mentioning, is to then kind of just decorate these arrows with the sort of conditional probability. Like once I say red, what's the conditional probability that the next word is going to be idea or birthday or something like that? So you can decorate these arrows with that. That's the intuition, and that's just kind of telling you what goes with what together with statistics. That's like syntax. Okay, so this is what we're kind of calling the syntax category, and there's nothing really more to it. Okay, it's just kind of like this bare bones skeleton thing. But if you want to know something about meaning or semantics, like what is it that allows just this data, what goes with what together with statistics, to then be used as input to a language model and then generate meaningful text? What's going on there? Well, first of all, the string red, R-E-D, that's nice, but like, what's the meaning of it? Well, using inspiration from the Yoneda Lemma, it'd be better to replace the word red by its Presheaf or representable functor, or depending on which way the arrows go, it's called a co-Presheaf. So in other words, instead of thinking of the word red, think of all of the expressions that red sits inside. That's kind of like the meaning. That may seem like a lot. Like if we had started this discussion by saying, oh, instead of red, think of all the things that sits inside, you might think that's too much. But it's not. Category theory is like, it's super simple. It's just the representable functor according to, corresponding to red. So that's the idea that you want to do. Instead of just looking at this category of language, you want to look at, let me write it like this. I don't think we want an op here. I want to replace each expression with its representable functor. So in other words, instead of red, I'm going to map red now to, I'll use this Hom notation, red comma blank. Okay, so the blank you can stick in an expression. And so this functor tells you, oh, does red sit inside there? Yes or no, yes or no, yes or no. The idea though is, we just said yes or no is not enough. Like this Boolean thing is not enough. You actually want probabilities. So you can actually think of this output of this functor, rather than being a set, what we do is that we replace set by another really nice category, namely the unit interval. This is a category because it's a preordered set, right? Real numbers, they have this total order. So that's how we're viewing the unit interval. So in other words, for every expression in the language, like rows, rather than getting just a set that indicates yes or no, does red sit inside red rows, you actually get a number, which is the conditional probability of that happening.
Right.
So another way you can think of it, like this representable functor now associated to red it's like the conditional probability distribution on the set of all strings, where the kind of components are the probability that string extends that word. So that's, I think, very intuitive. It's just that it happens to fit very nicely into all of these ideas that are already there in category theory. It's like you just pull them off the shelf.
I see. Okay, but that's
And
still,
then,
so this is still syntax, right? Because statistics is syntax. So is there, at what point do you draw a distinction between syntax and semantics?
yeah, so the point is here at this arrow. So on the left-hand side, we would think of that as syntax, but on the right-hand side, we would think of that as semantics, in the sense that the meaning, using first quote, the meaning of a word is its context or the company that it keeps.
Sorry,
So like
do we already
yeah.
have semantics in, sorry, is the object on the right-hand side, is that already the stuff with all the conditional probabilities, or is there something on top of that as well?
Okay, so this is notation for a category whose objects are these functions from this language category into the unit interval.
Mm-hmm.
And I specifically want to think of, I guess I should say, the image of this function. Sorry, the image of this functor, which is really like this Yoneda. This is like the Yoneda embedding. For every object, I get a representable. I would really like to think of the image of this Yoneda embedding. I guess this is like my semantics. In other words, I'm mapping each word like red to one of these representable functors, red, Hom, red, comma, blank.
Mm-hmm.
Loosely speaking, that's kind of like where we think semantics should lie, because this Hom of red, comma, blank is telling you the sort of conditional probabilities for which sequences will extend red.
Mm-hmm. So I think, how do I say? Are you saying that, how do I say? So if you train a large language model and it learns language quite well, like we have right now with GPT-3, it learns a particular instantiation of a probability distribution. So there's all these arrows. It assigns particular numbers to certain arrows, you know, whatever. I'm going to walk my dog. There's some number to that. But you're saying that if you want to take a step back as a category theorist and say, what is the space of all possible assignments to these arrows and where these things live? That's what the point of this work is, like the space in which all these assignments live. Is that roughly what's going on?
Perhaps leading there. Let me maybe say something a little bit else that might try to make this idea a little bit more believable. Mm-hmm. One thing about these language models is that, you know, you string together concepts and you get new concepts and you get this nice coherent thing. The thing is, you can't really combine ideas in just this category of strings. I mean, like I can have red and blue and I can concatenate them. That's extra structure. So maybe I have like a monoidal category or something. But what's the meaning of this new thing, right? Or what does it mean to say I like cats and dogs? Mm-hmm. Like I like cats and dogs and sheep and cow and blah blah. Oh, she must like animals. Like what's the concept of an animal? It's like the union of all of these things somehow. Or, you know, I like broccoli or ice cream. So how do you have like this notion of and or logic or this way to build concepts given like the meanings of words? And the thing is that there's a category theory provides a nice way to think about that. Not in just the normal category L. You only have this extra structure in this Presheaf category or this co-Presheaf category. And this is true in general. In a category C, it may be nice, but it may not have a lot of structure. You just said it has objects and morphisms and whatever, like we've been talking about. But you may ask for a way to combine objects to get a new object. Oh, can I combine expressions to get a new expression that has a new meaning that's built out from the individual meanings? A plain old vanilla flavored category may not have that. But it turns out that the category of presheaves or co-presheaves, if I take off the op, this is a very rich category. It has a lot of structure. You can combine things in this Presheaf category in a way that you cannot combine them in the original category. And what I mean, the words I'm using now, I'll just say them quickly and then we can forget about them.
You can write them too so that people can look it up, but yeah.
Okay, so the ideas I'm referring to are these things called limits and co-limits.
Okay.
So in math, you have very typical ways of building new objects from old objects. Like I can take two sets and multiply them. That's the Cartesian product. Oh, I get a new set. I can take a set and like quotient it. I can take two sets and take their disjoint union. So all of these kind of typical constructions, they are subsumed by a concept called limits and co-limits in category theory. But the idea is you may not be able to do that in a normal category, but you can always do that in the Presheaf category, it turns out. So it's like in linear algebra, sets are nice, but functions on sets have so much structure. Functions on sets are vectors. You were saying that. So you can work with sets or you can work with linear algebra, and that's by passing the functions on sets. It's the exact same thing here. You have so much more structure when you look at functors on the category valued in some other category, not just the category itself. So that's what we do. It turns out we have not just a normal category, but this specific one of language. And we're looking at these representable functors corresponding to words, and then we end up replacing set by probabilities because it turns out to be a little bit better. And over here, you can compute what are called products and co-products. So these are examples of limits and co-limits. So products and co-products, which is to say you have a notion of and you have a notion of or in this category that does not exist in the kind of skeleton category.
Let's just clarify this, because of course naively there is a notion of and or at I suppose like you can concatenate strings or intersect strings, and that's some kind of and or, right? But this and or is some different, more powerful and or, right?
That's right. The thing is, the operations you were just mentioning, like, yeah, you can do that, but that's additional structure on that category, right? Like category does not come with a notion of combining objects.
That's right.
You just have, right? So you can ask for additional structure, okay? Or you can say, oh, does my category have all products? Like if I take the product of two objects, is that another object, etc. So categories like that, they have names. It's like a complete category. Oh, one with all limits.
I see.
So the point is that not every category may have those nice properties.
Okay.
So if you don't want to worry about that, just pass to one that you are guaranteed has all.
Okay, I think I see where this is going now, and this is maybe a good place to wrap it up because this is going to extend a long rabbit hole. But here's the point. So we've only scratched the surface of category theory. I mean, we did a lot, but that's just you have an entire book on category theory, for example. But there are many operations in category theory, like product, coproduct, which also formalize standard operations in mathematics in the same way that we formalize things with functors and things like that. And the point is, because there is this category called L, and because you can enrich it with probability distributions, then as soon as you make that mapping to a category, now you can say, we have this category theorist toolkit, and let's apply all the different tools to see what we get. And so I guess your paper, or there's maybe more work coming out of it, is what is a product in this category? What is a co-product in this category? What are all these other things? And then you could interpret that semantically or whatnot. And that's kind of the point. Is that right?
Yeah, that's the point. And it turns out it's not just like, oh, let's see what we can do, but it turns out to give you things like that you would expect. Okay. So it's almost like if you were to take, the product or the and operator between two words or the representables for two words, you basically get something that looks like the truth table for and.
Okay.
And same thing for or. So it's very consistent. It kind of matches what you would hope would happen if you have a framework that would do something very useful, and it turns out to work out very nicely. So.
I see. And I'm guessing what you get is more like, because you could just, you could naively concatenate like the string dog or and cat in L, but that doesn't necessarily mean much in the world of strings. Yeah. Or you can think about or in some logical space, and that means that's much more captured in this category on the right-hand side.
Exactly, exactly. This category on the right-hand side, in this special case, when you're looking at presheaves on an arbitrary category, that forms what's called a topos. And topos theory is a really nice place to do logic. So that was kind of the inspiration for that.
I see.
And it turns out
Wow.
things go hand in hand really well. Yeah.
Okay, I have no idea what a topos is, but I guess it's nice to end on a cool buzzword to inspire people to learn more about the subject. Wow, well, great. This was so much fun to talk about. You know, I have to say, there's a part of category theory that I like. I like things to be concrete, so I don't go too deep. But it's there is a nice rigidity to it, in that it captures a lot of. You know, once you learn enough mathematics, I think you need a certain level of familiarity and depth of mathematics before maybe you can appreciate category theory. So it might take some time for people to appreciate, but I hope, you know, what we talked about makes that easier.
Yeah, I hope so too. Thanks so much for having me on the podcast. So if folks are interested, maybe I should just say the name of the paper if they want to learn
Okay,
more.
sure. Yeah, I'll just put the link also as well.
Great.
Yeah.
Okay, great.
Great.
Perfect.
All right.
Okay,
Great.
thank you, Tim.
Thank you so much. Yeah, have a good one.
Thank you. You too.